Hello there, and welcome back. Wherever you are, whatever kind of day it's been, you can rest now. Let your body unwind and your mind drift outward into the quiet of space. Tonight, we're going to follow the life of a star, from its first moment as a whisper in a cloud of gas, all the way to its final breath as light fades into darkness. This story stretches across billions of years, and yet, right now, in this very second, somewhere in the Milky Way, it's happening again. A new star is forming. Another is dying. The universe is never still. It breathes just like you. In the deepest parts of space, far from the heat of suns and the motion of planets, there are clouds, vast, cold, and dark. They float between the stars, almost invisible, made of hydrogen, helium, and dust finer than smoke. These are molecular clouds, the wombs of the cosmos. Each one stretches for light years, but inside, temperatures fall so low that motion nearly stops. Yet gravity never sleeps. Over time, it begins to pull the gas together, gathering invisible hands of mass around invisible centers. Slowly, gently, atoms fall inward, forming denser regions called cores. If you could drift there, weightless, silent, surrounded by starlight so faint it's barely a memory, you would feel nothing at first. But slowly, pressure would rise, density would climb, the darkness would fold into itself, and deep within that silent sea, a small point would begin to glow. That glow isn't yet a star. It's the beginning of one. The heart of a protostar, a forming sphere of heat and light that hasn't yet ignited fusion. The journey has begun, but it's still hidden from sight, wrapped in veils of gas. These places are called stellar nurseries. They exist all over the Milky Way. The Orion Nebula, for example, is one such nursery. A glowing cloud of hydrogen about 1,300 light-years away, where hundreds of young stars are still forming. The Eagle Nebula, famous for its pillars of creation, is another towering columns of gas stretching for light-years, sculpted by the radiation of newborn suns. Inside them, countless points of gravity are tugging inward, each one a seed of light waiting to bloom. And as gravity tightens its grip, the cloud begins to change. Collisions between gas particles heat the core, turning gravitational energy into thermal energy. The temperature climbs. What was once just cold hydrogen becomes something restless, shimmering, nearly alive. At some point, the pull of gravity and the outward push of heat reach a fragile balance. The cloud fragments into pieces, each one collapsing toward its own destiny, its own star. If you could watch this from afar over millions of years, it would look almost alive. Dark patches of nebulae twist and shimmer, folding into bright knots that begin to shine from within. The faint glow is not yet nuclear fire, but compression, the slow friction of atoms falling inward. And when one of those knots reaches enough density, something profound happens. The inward fall of gravity becomes unstoppable. The center compresses until it's hot enough, millions of degrees, for hydrogen atoms to begin fusing into helium. Fusion is the secret heartbeat of the universe. It's the reason stars shine. When hydrogen nuclei merge, they release energy, light, heat, and radiation. That energy pushes outward, fighting against gravity's inward pull. When those two forces balance perfectly, the star stabilizes. It's born. But before that ignition, there is chaos. The forming star is surrounded by a swirling disk of dust and gas. Some of that material falls in, feeding the young star. Some of it is ejected in powerful jets along the poles, streaming out into space for light years, clearing the surrounding gas. These jets are called Herbig-Haro objects. Brilliant, thin beams of matter that mark the birthplaces of stars like cosmic signatures. Around the protostar, planets are already beginning to take shape. Dust grains collide, stick, and grow into pebbles, rocks, and eventually worlds. Inside the nebula, thousands of stars might be forming at once. Some are tiny, future red dwarfs that will burn dimly for trillions of years. Others are massive, blue-white giants that will live fast and die young. Their light will soon carve away the gas that birthed them, erasing the nebula itself. The nursery that gave them life will vanish under their brilliance. This is the paradox of creation in space. Every act of birth is also an act of destruction. The same radiation that lights the universe also tears it apart. But without that light, nothing would ever grow. Over time, as the gas disperses, what remains are clusters of newborn stars, still close together, bound by gravity. These are open clusters like the Pleiades, where dozens or hundreds of stars share a common origin. Eventually, they drift apart, each taking its own path through the galaxy, carrying with them the chemical fingerprints of the nebula that made them. A protostar is a star in waiting. At this stage, it's a sphere of dense gas that hasn't yet reached equilibrium. The interior is heating rapidly, but it's still wrapped in thick dust. From the outside, it glows in infrared, invisible to the human eye, but detectable by telescopes. Inside, pressures are rising, atoms moving faster, collisions growing fiercer. When the temperature at the core passes about 10 million degrees Kelvin, hydrogen begins to fuse. In that moment, a new star awakens. The fusion of hydrogen into helium releases enough energy to counteract the inward pull of gravity. The star stabilizes. It stops collapsing and begins to shine. From this point forward, it joins the main sequence, the long middle chapter of stellar life. Young stars often flicker and flare as they adjust to balance. Some have strong magnetic fields that fling material outward in bursts. Others pulse as their outer layers expand and contract. But over time, most settle into steady rhythms. The wild light smooths out. The chaos becomes calm. If you were floating near one of these newborn stars, you'd see an accretion disk still glowing faintly, spiraling inward. Beyond that, smaller clumps of rock and ice are beginning to form planets. It's likely that every star in the sky once looked like this, wrapped in dust, burning into being. Even our sun had such a past, around 4.6 billion years ago. Its disk gave birth to the planets, moons, and asteroids we know today. When we look at other systems forming around distant stars, we're peering into our own origin story. The same forces that shaped them shaped us. The same hydrogen atoms that now fuel those suns once drifted through dark clouds just like the ones we began with. Once a star reaches the main sequence, it settles into a kind of cosmic adulthood. The chaotic birth is over. The balance between gravity and radiation is steady. The core burns hydrogen into helium at a constant rate, and the light that escapes travels across space for billions of years. For stars like our Sun, this phase lasts about 10 billion years. For smaller stars, like red dwarfs, it can last hundreds of billions, longer than the universe has yet existed. For massive blue stars, though, the main sequence may last only a few million years. They burn through their fuel so quickly that their brilliance is also their doom. The color of a star reveals its temperature and mass. Red stars are cool and dim. Yellow stars, like the Sun, are warmer and moderate. Blue-white stars are hot and intense. The spectrum tells us where they are in life and what their fate will be. At the heart of every star, hydrogen atoms collide under immense pressure, forming helium and releasing energy according to Einstein's equation E equals mc squared. Only a tiny fraction of mass is converted into energy, but that's enough to make stars shine for billions of years. The light you see from the night sky is the direct result of this conversion. Matter becoming pure energy, radiating outward. Inside, convection currents rise and fall like boiling water, carrying energy from the core to the surface. On the outside, the star appears calm, but within there's constant movement, waves of plasma and magnetic fields, storms and flares. Even the sun, steady as it seems, pulses faintly with sound waves deep inside, ringing like a giant bell. During this long Middle Age, stars maintain a delicate equilibrium. The pull of gravity tries to collapse them. The pressure from fusion pushes back. That balance defines the main sequence. When hydrogen runs low, the balance begins to falter, and change becomes inevitable. Even stable stars aren't truly still. They breathe in slow rhythms of expansion and contraction. Some grow slightly brighter or dimmer over days or years. These are variable stars. Their light pulses as their outer layers expand and cool, then contract and heat again. The most famous are Cepheid variables, stars whose rhythmic brightness helps astronomers measure cosmic distances. By comparing how bright they appear to how bright they truly are, we can gauge how far away their galaxies lie. Our sun also varies, though subtly. Its brightness changes by small fractions of a percent due to magnetic activity and sunspots. Every 11 years, the solar cycle peaks and wanes, marked by flares, prominences, and auroras on nearby worlds. These changes remind us that even something as steady as a star is still alive with motion. Stellar winds, constant streams of charged particles, flow outward from nearly every star. They shape entire systems, pushing away dust and sculpting magnetic bubbles around planets. In massive stars, these winds can strip away outer layers, reducing mass and altering evolution. When we look at the night sky, we see stability, but in truth, it's a grand illusion. Each point of light is in flux, expanding, contracting, trembling, flaring. Every star carries within it the story of struggle and balance, energy and exhaustion. And sooner or later, that balance will fail. When a star's core runs out of hydrogen, fusion begins to slow. Gravity starts to win. The core contracts, heating up further. The outer layers expand, cooling and reddening. The star swells into a red giant. For stars like our sun, this transformation is dramatic. The radius can grow hundreds of times larger. The surface cools, shifting from yellow to deep orange or red, while the core burns hotter than ever. Inside, helium begins to fuse into carbon and oxygen through the triple alpha process. This stage is brief compared to the main sequence, lasting only a few 100 million years for sun-like stars. Massive stars, on the other hand, become red or blue supergiants. They can grow to sizes so vast that, if placed in our solar system, their surfaces would reach beyond Jupiter. Betelgeuse, a red supergiant in Orion, is one such example. A star so enormous that its light pulsates visibly across months. Inside its vast core, fusion proceeds furiously, creating heavier and heavier elements. Carbon, neon, oxygen, silicon, all the way to iron.